So exciting. So when I was in school, I went to a lot of presentations, and one of the things that I learned is that back in ancient times, not ancient times, but medieval times, there was a lot of torture going on in medieval times, right? And out of an activity that you participate in, often traditions often come out of this, right? One of the traditions in medieval times is that the torturer would show the implements of torture to the torturee. So these are some of the things that I'm going to be torturing you with tonight, some of these graphs and statistics and numbers. And this one particularly, this was particularly painful. So just so you guys are all aware of what's happening, I think that we can use that. Just keep that in mind as we're moving forward. Some of this might be just ever so slightly painful. Anyhow, welcome. Thanks everybody for coming out on a cold solstice evening. Happy solstice, everybody. I am Reuben. I'm the environmental coordinator here at Skagway Traditional Council. With me as always is Colton Belisle. He's our program assistant. We've been running this air quality study for the last 3 years, and we're really excited to have these results for you here tonight. We're not just going to go over 2022. We're going to be looking all the way back to the beginning of the study and going over everything. And as I usually like to have, I'd like to have a little bit of a guide, a map, if you will, to the evening's festivities. And just so you know, the doors will be locked after this slide advances, so this is your last chance to bail. So we're going to go over air pollution, right? Because I'm assuming that we all have kind of an idea of air pollution, but does anybody know what PM 2.5 is? Okay, that's perfect. So we will be going through a little bit of the science. We're going to take this kind of 10,000 foot view, look at some definitions, and hone in kind of specifically to this one particular aspect of air pollution. We're going to talk about its health effects, some of its sources. We're going to zoom out just a little bit, and we're going to look at the regulations that have been put in place by the federal government, and then we're going to look at the equipment that we use to measure this particular type of pollution. Then we'll just briefly go over our study design. We're going to have an awesome equipment demo, and finally we'll get to the results. And then we've got some exciting things to talk about in the future, some stuff that just came up at the end of the summer this year that we've been talking about over the last couple of presentations, and kind of waxing philosophical about like, ooh, what could be possible? Well, there are some things that are possible. We're very excited about this. So, that right? Looks like we're all staying in our seats, so let's just move right on in. The environmental department has a lot of different types of programs that we implement, and all of these are based off of tribal citizen assessments and strategic planning meetings and council oversight conversations among staff. And over the last several assessments that we've put out, air quality is rated very high. This makes sense. If you spend the winter and the summertime here, you can tell that there's a difference in the air quality going from winter into summertime. Some folks feel the effects more than others. I've talked to a lot of folks that say they have a hard time coming downtown, going down to the harbor front during the summertime because they have asthma or cardiopulmonary disease or some sort of pre-existing condition that makes it more difficult for them to breathe. So it does make sense that air quality has been a top priority issue for tribal citizens. And so this study was concocted back in 2018. We've done indoor air quality in the past, and then this is kind of the outdoor air quality facet of that. So, with that in mind, we have to kind of think about, so what exactly is air pollution? What is air quality and what is air pollution? Air pollution is basically just airborne particles of various different types of compounds that can have deleterious or detrimental or bad effects on human health, on ecosystems. So, the World Health Organization back in, what was that, 2018? I haven't seen a new figure, but back then they made this estimate that approximately 4.2 million deaths occur annually worldwide prematurely because of some sort of air pollution, but particularly ultrafine particulate matter. And that's why we've got this wonderful acronym up here. We're not talking about the time of the day here. We're talking about particulate matter. It's exactly what you might think of. The definition up there, it's a term for a mixture of solid particles and liquid droplets found in the air. Right? It could be made up of this, that, or the other, just about anything. But when we start to define particulate matter, there's a number of different classes, and these are all classed based on size, right? And when we start talking about size, we're going to be getting into a little bit of this metric system stuff. And Don't worry, don't get confused. I'm not going to make you do this math problem. I'm not going to make you do the conversions. We're going to use our lovely little graphic right here to try and depict what we're talking about when we're talking about a micrometer or a micron. A micrometer is basically a very small meter, and a meter is basically a really strangely shaped yard. So, but I find it helpful to use one of these lovely graphics so we can all picture a grain of fine sand, not Skagway sand, not like we find in the beaches here, because that's going to be up in the meters range. We're talking about fine beach sand like you see in California or Hawaii. That's 90 microns in diameter, which is roughly 0.004 inches, but tangible, something that you can picture in your mind, and here it is all blown up. And you can all probably picture a human hair, right? You've probably rarely seen it like this, but this is about 50 to 70 microns in diameter. So when we start talking about particulate matter, PM10 is 10 microns in diameter, and PM10 is the very first size class of PM that is actually regulated by the government. And the reason for this is because PM10 is something that you can inhale. It can get into your lungs and it can start to affect you physiologically. It will start causing inflammation. We've all probably inhaled some dust or pollen or mold, and it's caused, probably not a good effect in many of us. So you can see that kind of wrapped around the human hair here, these little blue balls. But more important and much more dangerous to human health is PM2.5. These are 2.5 microns in diameter. You can see them kind of wrapped around the little blue ball here. And the reason these are more dangerous is because not only can you inhale these, but their size is so small that they can cross cell walls and they can enter your bloodstream and they can start affecting you in a deeper physiological way. And we know this because of the science. Lots and lots of science has been conducted on the study of particulate matter 2.5 microns and smaller. For example, Xing and all of their friends did this study where they were looking at what happens when you introduce the human body to various levels of PM 2.5. And for every incremental increase of PM 2.5, they found greater hospitalization rates, they found lower lifespans, a higher propensity for lung cancers and cardiopulmonary diseases. This graphic up here, I included it in this, and I didn't actually pay attention to the R squared, and anybody who knows the math knows that R squared is pretty poor. But there is a loose relationship in this. On the x-axis here we have concentrations of PM 2.5, and on the y-axis we have death rates from lung cancers. And there is this kind of loose relationship. For every increase in PM 2.5, they found that death rates would increase. And down at the bottom here, this is a graphic that talks, it was a lab experiment with rats, where they were exposing rats to different levels of PM 2.5 and then investigating whether or not their lung infection rates went up or down. And of course, the more they exposed these rats to PM 2.5, the 4-fold to 8-fold more lung infection rates were seen. The EPA also has a huge list of different deleterious effects to human health, decreased lung function, chronic bronchitis, cardiac arrhythmias, premature death. But what we need to pay attention to is this bottom portion of the graphic, is sensitive groups. This is a big healthy part of the population, right? People that have heart or lung disease, older adults, children, pregnant women. They're gonna have a different experience when it comes to exposure to PM 2.5. And I've been reading studies lately that have been kind of re-examining some of these regulations that we're going to talk about in a little bit. And kind of the conclusion that we're coming to now with the current science is that maybe these regulations aren't taking these more sensitive groups into consideration. We saw this summer when we had wildfire smoke come into Skagway, and according to our machines, the air was still healthy for most people. But all of the asthmatics and the more sensitive people that are in this sensitive group were complaining about having trouble breathing and needing to use their inhalers more and just not wanting to go outside. So it's possible that we need to revisit these regulatory limits as we move forward. And hopefully that's something that's going to happen, and we'll talk about that, because air quality monitoring is becoming much more accessible to a larger body of the population, which is great. What about environmental effects? Well, obviously, the most obvious effect is going to be haze, right? This is up at the pass this summer during that wildfire smoke event. But does anybody remember acid rain? Remember the scare of acid rain? Like, what was that, back in the 90s? As a kid, I always pictured like getting rained on and having my face melt off, but of course that's not the case at all. What we're talking about has more to do with the balance of pH in aquatic systems and the interaction of the atmosphere with, say, our crops. Acid rain is a result of too much sulfur dioxide and too many nitrogen oxides chemically combining with the water in rain droplets and then lowering the pH and then falling to the ground and going into these aquatic systems. It makes it much more difficult for salmon and salamanders and snails to make a living in those aquatic systems. It also can affect our crops and our trees. When this acidic rain, this acidic water falls on our crops and our trees, our forests, it's going to cause defoliation, it's going to cause all sorts of problems. Nutrient balance in the soil can get altered. And acid rain is actually so bad that it can affect our infrastructure as well, because certain types of buildings are made from materials that will be wasted away more quickly if a low pH or a highly acidic liquid is in contact with it. And they found this out. So it's bad for us, it's bad for the environment, and it's bad for our infrastructure too. This is stuff that we should be paying attention to. So when you think of PM 2.5, what you should think of is combustion, because that's going to be a major source for this stuff. So sources in Skagway, of course, everybody's probably going to jump immediately to cruise ships, and I think a lot of us have seen this graphic from the Park Service. It shows 4 ships in port, and this terrible, awful-looking haze is kind of sitting down at a pretty low level. But cruise ships aren't the only thing that have internal combustion engines, right? We've got trains. And trains, we need them, but they are burning fuel in order to make their living. So they're contributing to our poor air quality. Coach buses and the smart buses and vans and all the transient vehicles coming in from the seasonal workers, these are all burning fuel. When we go over to Dyea and we have ourselves a campfire, this is from last summer, the air over there was full of smoke, and that's combustion, that's PM 2.5. And anything that's going to be burning fuel, anything that's going to be combusting is going to be contributing to this. So lots of potential sources here in Skagway, and we can definitely see that these sources are going to increase in summertime because we have this influx of boats and trains and people in their cars, people having campfires, wildfires. All of this stuff is going to contribute to a poorer air quality situation. So what is healthy air? Remember, we're talking about these benchmarks. Well, back in 1970, the Environmental Protection Agency, which has funded this study and is funding this evening as well, thank you EPA, they came up with the Clean Air Act. This is basically a body of legislation that regulates potential polluters and what they're allowed to emit out into the air. And the way that they can gauge that is by setting these standards. So what we have here are the two basic standards set by the EPA for PM 2.5, an annual average and a 24-hour average. Now for our purposes, it doesn't make a whole lot of sense to look at this annual average, because it would mean that we'd have to have these machines set up all year long to be able to just get our first metric. If we look at a 24-hour average, then we can get multiple metrics over just a single summertime. So it's much less work for us, and we can get more meaningful data that we could then compare to these standards. So does this figure make any sense to anybody? Looks like Greek, right? It's all just kind of garbage. That's because it is Greek. This is actually the Greek symbol mu, and that stands for micro. So we're again in the metric system here, and we're talking about micrograms per cubic meter. And this makes sense when we're talking about air quality in a way to measure, because as we breathe in, we're breathing in a volume of air. And then if we were able to take and analyze all the particulates in that volume of air, we could then estimate what the concentration of pollutants actually is, right? So when we're measuring this, we are taking a cubic meter, which is just a meter by a meter by a meter, that volume of air, and then we're basically putting it on a pseudo scale, and we're measuring how heavy all those microparticulates are within that. And we measure them in micrograms, which is just what you think. It's a very, very small, teeny tiny gram. And to give you an idea of how many micrograms are in a gram, I have included a teddygram, which weighs 1 gram. and there are 1 million micrograms in a teddy gram. So can you use your kitchen scale to measure this? Yeah, probably not. You have to have some pretty sophisticated machinery in order to do this correctly. Now, traditionally, what is done is you have an instrument that draws in a measured amount of air and sorts the particles. This is the black box magic to me. I don't really understand entirely how this works. It's something to do with the way vortices and different sized particles are interacting with a small volume of air. At any rate, this inertial sorting impactor assembly, you might know it as an impactor plate or an impactor assembly, is going to take and it's going to stick these larger particles onto an impactor plate and allow the smaller particles to pass through. Now, in a federal equivalency machine, which is going to be this higher grade monitor, these more expensive machines, these smaller particles are then collected on a little filter that's been pre-weighed, and then you have to use very precise scales to weigh that at the end of a predefined period of time, right? So if we're looking at trying to get to this 24-hour average, then we're going to need to have a 24-hour test to be able to determine what the total weight is per cubic meter. So that's great. It's expensive though. It's very, very expensive. I think an FEM machine introductory rate getting into it's like $80,000 to $100,000. Like, this is not an accessible machine to most folks, right? So, and this is a problem because air quality is such a widespread issue and it's so important to so many folks. It needs to be more accessible so more people can analyze what the air is that they're breathing. Clean air is a human right. We should all be able to breathe and function because it's just part of our living. It's part of what we do. So some very, very smart people to mitigate this problem have come up with a different type of technology called laser photometry. And don't worry, there won't be a test at the end of this, but there will be a spelling bee with prizes. So you're good. So laser photometry is based off of the same principle. You're taking a measured volume of air and you're pre-sorting these particles into whatever size class you want. You know, you can do PM10, you can do PM2.5, you can go all the way down to PM1, which would be 1 microgram. But we're using an inertial sorting impactor assembly to sort these pieces. But instead of collecting them on a filter, we're going to be putting them into a chamber. And this chamber has a laser. It's great. Science and lasers is fantastic. It has a laser that's pointed towards a little photodetector. And as this air enters into that chamber, the laser is going to interact with the different particles that are in there. And there's going to be a slight reduction in the intensity of that laser. And there's going to be some scattering, what we call refraction. And so the reduction of that intensity is measurable. And the angle of that refraction is measurable. When you combine the two of those, you can actually come to a very, very precise calculation of what these particles weigh. It's amazing. It's magic. And it also makes it much more accessible to the general populace. Have you guys ever heard of the purple air monitors? They're like these little cans. They're a couple $100, and you can put them outside your house and hook it up to your Wi-Fi, and then you have yourself a little particulate counter at your house. It's very, very accessible. It does fall victim to one central pitfall though, and that's the fact that this is all visual cues. And visual cues are not gonna fit the bill every single time. And a good way to illustrate this is with the old ping pong balls versus the old golf ball problem. If you present 97 ping pong balls and 97 golf balls to a human being and you ask, which one of these weighs more? We probably all know the answer, right? Which one's gonna weigh more? Golf balls, right? Because we know that the golf ball is a solid object, and we know that the ping pong ball is a hollow object. And so these two things are not going to weigh the same amount. But the laser photometer doesn't know that. All it sees is its size. So we're going to get some kind of skewed answers from that. So the way that we get around this, there's a couple of different ways. We can do what's called co-location, which is where you take one of those really nice, expensive federal equivalency method machines that cost $100,000, and you run that for 24 hours, and you take your laser photometer and you co-locate it in the same place. and then you compare your results after your 24-hour test. And the difference between those two results is now your calibration factor. So you can use that laser photometer moving forward in time and know that your calibration factor is going to compensate for this difference in weights. They also have done studies on this for years and years and years. So they have calibration factors for different things, including ambient 2.5. So this really only comes into play when you're doing a regulatory study, say you're in an industrial setting and you have a known compound that is airborne, and you need to know whether or not you are exceeding some specific limit. We're not doing that though. Bless you. What we're doing is we're asking the question, is there a difference between, is there an effect of a typical tourist season on the air quality in Skagway? We're not out there to regulate the cruise ships. We're not there. We are here just to answer that simple question. Is there an effect of having all of these different sources of combustion in Skagway during the summertime? So for us, having a laser photometer absolutely fits the bill. It's perfect, and the EPA has approved this for our study as something that is going to be accurate enough to achieve our objectives. So we are using the TSI Dust Track 2. They're fantastic. We know that they work. This is not a consumer grade laser photometer like the Purple Air, because this also has one of those little gravimetric filters in it. So what we can do is we can co-locate this machine to itself. We just have to have that really expensive little scale to be able to weigh these teeny tiny little grams. So it makes this scalable. It makes it so that we can use these dust tracks in future studies. If we need to look at something specifically, we can go out there and we can get our little gravimetric filter going, and we can really hone in on some good stuff and then decide where to go from there. So at any rate, let's talk about our study design. It was originally concocted back in 2018 under the assumption that we're going to have a normal cruise season, and also under the assumption that we're probably going to run it for 1 to 2 years. So in order to tell whether or not no ships and lots of ships is going to have a difference, we need to start the study before ships show up, right? So it's slated to start in April, and it's meant to go all the way past, through the cruise season, and then past when the last ships leave and end in October. So that way we can look at October's data and we can say, okay, in October we've got nobody here, there's less stuff burning. How does that compare to the middle of the summer when we've got 4 boats going, we've got 20 trains going up and down, everybody's going out rafting in their vans, there's a smart bus every 15 minutes, all that stuff. So, makes sense, but of course things didn't work out that way. We didn't start the study until 2020, and we all know what happened then. But we'll get into that in just a minute. Location is also incredibly important, right? We want to have representation of what the ambient air is throughout Skagway. So I like this graphic because it shows the way that wind and air is going to interact when it comes into contact with structures, right? So if we're trying to get a representative location for our machine, we probably don't want to put it in the lee of this building because air movement might not be as much there, or it might be too much. We probably also don't want to set it up on the runway because there is a source of combustion there as the planes are taking off and landing. So locating where to actually put these machines, it takes a little bit of ingenuity, a little bit of trigonometry. Like, you have to think these things through because you really want a representative sample. And sometimes you have to move things around. So you also don't just want one location, right? Because if you have one location and it turns out to be a bad location, you've got a whole year of bad data. So we've got 3 locations on a southwest to northeast gradient, right? And part of the reason for setting it up this way is because, let's say our hypothesis is that the cruise ships are going to be the biggest emitter. We want to know, are emissions larger down by the cruise ships than they are up at the north end of town? Or is there some other source somewhere in town that's contributing more? So we've got these 3 stations. We've got one down in the small boat harbor. We've got one that usually sits just right outside here in the most open part in between the 2 buildings. And then we've got one way up at the north end of town that we actually had to move a couple of times. We found out that the first location, it was too close to the road, so it was running a little bit hot. We were getting some skewed results. So we moved it out of the way. We moved it over more towards the levee, and it seemed to stabilize a whole lot more. So we have what's known as a desktop unit. This is meant to sit inside on your desktop. It's got 2 internal batteries that'll run for about 16 hours. So is that going to work for our study? Probably not in its current state, because we need a 24-hour test, right? Because we want to compare it to that EPA standard. We also need to have it outside, because we're not measuring indoor air quality at this point. So we need to have a couple of add-ons in order to make this work. And so we thought it would be fun for you all to see what we go through on a regular daily basis, 7 days a week during the summertime for 6 months out of the year, actually. It's a lot of running time. So I'm going to bring our wonderful program assistant, Colton, up here, and we're going to check out a little demo of what we go through during the summers.
You can disappear?
This is a magic show.
See, it would have been better if Colton was under there.
Down on that. We'll have Darren lay down on the dust.
So looking at what we have for air quality, we have 3 of these blue cases, 3 of these gray cases, 3 of these tripods, and 6 of these rechargeable external batteries. And usually we'll start every other morning at 8:30. When it comes to setting up, they need to be set up by 10 every other morning. So we'll start about 8:30 and we'll usually be done around 9:15 with our setup. And the first thing we'll do is we'll come in, we'll open our 3 blue cases, we'll turn the 3 machines on, and we'll start our note taking there. What we're looking at in our initial notes is how easily they turned on and their starting battery percentage. And then we'll note their calibration. Moving over to our calibration is we'll just move them across the road to our, we have a little calibrating tube set up. We're measuring 2 things. We have our span potentiometer, which is like a volume control for your TV. That lets us control the LPM, the liters per minute that we have with the air intake. And ideally, we always want our LPM to be at 3, but we take between 2.8 and 3.2 in that ballpark of 3 LPM. And once we have all 3 of our machines calibrated to be in that ballpark, we'll note down what it started at, what we had to move it to if we had to move it, and then what that span potentiometer is at. And then once everything is looking good and together, we'll pack everything up, we'll load it into the truck, and we'll move to our first site. And then once we get to our first site, we will split off into 2. We'll have one person set up the machine, and then one person will take notes at the site and set up the tripod. And then once the tripod's set up, the case can be screwed on there. And then turning on the machine, the first thing we want to do is we have our 0 calibration tube, and the 0 calibrator just plugs right into the top of the machine, and then you can just start 0 calibration. It takes 1 minute, and that just gives it a nice baseline to start everything off of. And then while that minute is going down, I like to take these attachments and start setting up our blue case. We have the air intake that goes on the top. It just squeeze in. And on the inside, we have our bottle here to collect moisture. And then we have our air intake tube, and that just plugs in. And then once those are in, you can go ahead and move the battery in first while there's room for it. That can just be velcroed in. And then by this point, 0 calibration should be done, the minute should be over. You just let your note taker know that 0 calibration is done. They'll mark down that it has been finished and who did it. And then you can take your impactor plate, screw it in half, take your impactor oil, do 2 drops into the plate, reassemble it, and plug that into the top. And then once the device is all put together, this can be moved over and added to the tripod. And then once that's strapped in, we want to make sure that our battery is connected. We want to make sure that our battery is plugged into the machine. We want to connect our tube. And then we go back and triple check that everything's secured because we're a paranoid bunch around here. And then that's done for that, or there's one more step for this. But after everything's plugged in, we have everything double checked, everything's secure. We'll go into a survey mode where we'll run a test run and just make sure everything's running good, make sure it's not reading negative, and get kind of an idea of what's going on in that instant. And then once the survey's done, once the survey looks good, we'll move it back to its normal operating test that will schedule it to automatically start at 10 a.m. So then all 3 will automatically start at 10 a.m. and they'll all be synced up for the 24-hour test. And then once that's all done, we'll close the case up, we'll lock the case, and then we'll finish notes. And when we're taking notes on the site, what we're looking for is we are looking at the temperature, wind direction, wind speed, cloud level, rain level, and then we'll be looking at observations such as anything that might affect you in the area, like heavy traffic or ongoing construction, anything out of the normal, and then we'll just be observing how visible the mountains are, the cloud levels. And then that's it for each site. We'll come back 24 hours later in the next morning, at least at 10 a.m. And then we'll get to the site, we'll open our case back up. We'll take the same notes as we did during setup, but this time we'll also be writing down the min, the max, and the average readings from the last 24 hours, as well as how much battery is left on it, and get an idea of how our batteries are doing. And then once we finish disassembly at each site, we'll take everything back to the lab. And once they're there, we'll once again be splitting off into 2. And we'll have one person take each of these impactor plates, and they will be disassembled, and then those will be cleaned and with Q-tips or rubbing alcohol, and those will be left to dry out and dry over the rest of the day and overnight, where they'll be ready for setup in the morning. And the other person will be taking the machine, and they'll be having 2 backups of the data. We'll have one backup on the computer, and we'll have another backup on a hard drive, just to make sure we have everything double back up. And the machine will be wiped to prevent future corruption, future confusion, and batteries will be swapped. New battery will go in, old battery will come out to charge. And then that's it for takedown and setup. And that is our every other day pattern when it comes to our air quality machines.
You sound like you've done that a few times.
Once or twice.
Once or twice. This guy has actually done this the most out of any of the staff that I can see. You've been doing air quality since 2020, right?
3 summers, 2,
Yeah.
3 summers.
Yep. So 2021. So yeah, so Colton's definitely had some experience setting up. We also have another person in the crowd here that has done this so many times. You've done it for a whole 6-month period. Thank you, Wyatt, for all of your hard work this year. You made it possible for us to actually get to the point where we're looking at our data. But let's talk a little bit about experimental design, shall we? Do you get as excited as I do about experimental design? Oh boy, it's so exciting. Let's say we've got 2 plants, right? And what we want to find out is does watching SpongeBob SquarePants cause your plant to grow faster? How would you do this? What would you do? You probably want to set up two different groups of plants. You would have a control group and you would have a treatment group. Both of these groups would get the same amount of sunlight. They'd get the same amount of water. They would get the same temperature. But the control group is going to sit in the corner by itself, and the treatment group is going to sit in front of the TV and watch SpongeBob all day long. And you're going to measure that plant's growth from day one all the way to however many days you want to do it. And at the end of that study, you're going to look at the graph of what the plant growth looks like. And you are going to be able to say with a certain level of confidence that, yes, my hypothesis was supported, or no, my hypothesis wasn't. According to this graphic, plants love SpongeBob SquarePants, but you put whatever treatment you want into that. This is easy to do if you're sitting in your house or if you're in a laboratory, but it's a lot harder to do when you're out there in the real world. It was definitely a difficult thing for us to do with our particular question, which is, does a typical cruise ship season have an effect on air quality? We can't go out and tell the cruise ships, hey, could you just take a summer off? Because we really want to know what the air quality looks like when it's just community contribution, right? That would be crazy and wild. But then we had 2020, when it was just me and my air quality machines out there hanging out with the beautiful, pristine, clean air of Skagway. It was this beautiful, unprecedented silver lining to an otherwise terrible experience that allowed us to capture this community contribution so that we know what it looks like when we don't have a bunch of seasonal migrant workers coming through here and bringing their cars, when we don't have cruise ships sitting out in the dock running their engines all day, we don't have trains running 24/7, right? 2021 was another kind of unprecedented year because we didn't really have a full season. This was our first ship of the year, and we had a few of those, and we had a few more, but it really wasn't anywhere close to even a partial season. I would call it cruise season ultra light. And then we had 2022, which was meant to be, the better part of a full cruise season. We still had some caveats there, right? We still had some COVID restrictions, so the ships weren't at full capacity. And then, of course, we had the Rock of Doom, which put a total damper on the amount of ships. So if you compare 2022 to 2019, 2019 had 450 plus ships. We only had a handful over 200 ships in 2022. So it's still at about, at best about 50% capacity. So ideally what we'll do is we'll run this study one more time. But we do have this wonderful control group of 2020 and 2021 I kind of still count as a control group because it was such a low volume season. And then we've got kind of, the halfway mark. And then hopefully we will see a full season next year and we'll be able to look at the data from that one here. So that brings us finally to our results. You guys have sat through many, many minutes of lots of fun and awesome, beautiful science, and the torture is about to begin because I'm busting out the graphs here in a minute. But first, a couple of metrics, because I think that this is a pretty impressive thing when you look at it all together. That setup that Colton just showed you, how many times do you think we did that over the 3 years of study? Any guesses?
600 times.
Very close, 785 setups. We analyzed 3.4 million liters of air. We took 1.3 million samples. We made 12,560 environmental observations, and we performed 3,925 calibrations and quality assurance checks to make sure that these data that we've collected are legal, defensible, and beautiful and pristine. Every single one of those observations and all of those metrics are all written down in a field book. And then, our very happy tech and assistant staff gets to digitize that. And it's such a fun and lovely process. It takes days and days and days. And then our lovely environmental coordinator gets to go through and validate those data and do all the statistics. The reason that it's important to put the data into this format is because then we can export it into a statistical program so that we can look at everything and we can take and say, hey, I want to know if the average PM 2.5 for this year at this particular station, if there's any correlation to the wind speed, right? And we can make a graph and we can set some hypotheses and we can start to do some statistics on it, right? And so then we get to the results. This doesn't make a whole lot of sense, does it? Right? If you're looking at it all together, we've got 2022 in the dark black line, 21 is in the dashed line, and 2020 is in the gray line. When you smash all this stuff together, it's a great idea, and you think you'd be able to see stuff, but you can't make any inferences from this. All you can see are different events, right? 2020, there was a big old spike. We see lots of different spikes. 2021, there's this big one. This is this wildfire event that happened this year. But you can't tell just by looking at this, is there a difference between 2022 and 2021? So enter the wonderful world of statistics. I can't wait to tell you about my kurtosis, I'm telling you. Statistics comes into play because what we can do is we can help to tease out whether or not what we're seeing is the result of something that happened by chance, something that happened randomly, or whether or not we're looking at something that happened for a reason. And we do this through hypothesis testing, right? So our null hypothesis, or the hypothesis that we're trying to disprove, is that there's no difference in average PM 2.5 between the years. And our alternative hypothesis, what we're setting our test to, is that there is a difference, right? And for anybody who's watching online, this isn't actually online right now, but here is the proof. There is a difference between some of these years. That's a significant p-value for those who love statistics like me. But, say again?
What's the number?
Oh, the p-value for the difference between 2022 and 2021 is 5.29 to the negative 11th. So that's a 0.00000000005 as a p-value. So that is absolutely a significant difference. But that's a little hard to digest. That's not an easy thing to really think about unless you just love math and statistics. Which some of us do and some of us don't. So for those that don't love the statistics, here comes the torture. Here is the graph. So the graph is organized into years, right? We've got 2020, 2021, and 2022. And each of these bars is a different station. We've got the South Station at the harbor here, the STC station here, and the 21st Street station here. Notice a difference between 2022 and these other 2 years. That is statistically significant, and we have that's statistically significant. So, but the graph helps to visualize this, right? We didn't see much of a difference between 21 and 2020. And I attribute that to the fact that there really wasn't much of a transient population in town. We weren't running a whole lot of trains, and we really didn't have a whole lot of cruise ships in town. Even though we had them coming through, it was at quite a minimum. And statistically, there is no difference. Like any difference that might happen between these 2 years probably happened by chance. But compared to 2022, both of these years were very different. So we have answered our central question. Does a typical cruise season, or at least 50% of a cruise season, have a negative effect on air quality? And we can say yes. And so that moves us forward to our next step. But I like to, we collected all these other data. So if we break it down and we look at some other things, let's think about, is there a difference between having one ship and having 4 ships? Turns out there is. These are the data from 2022. And as you can see, with one ship, we're hovering right around 5 micrograms per cubic meter. And with 4 ships, we're hovering closer to 11. And it's a very linear relationship between the two. And it'll be interesting moving forward to see if this same trend continues, to see if we see the same thing happen again. There's all sorts of factors that could come into play that could skew these results. But for preliminary, we do have some significance here, which I think is very interesting. So we've got environmental variables as well, right? Wind speed is one of the ones that sticks in my mind, which makes sense. If you're talking about particles that are aloft in the air, if you have a lot of air movement, say from a heavy wind speed, you're probably going to have less particles in your final count. And the data support that. Roughly. We're not collecting continuous data. It's categorical data. We're basically saying, what's the wind look like? Is it on a scale of 1 or is it on a scale of 6? And Wyatt's taking his interpretation of what could be a 6 for me, but he's saying it's a 5, and Colton might say that that's an 8. It's all, we're trained to look at the Buford scale, which is what this scale is that we're looking at, the 0 through 8. But there's every chance that there's going to be what's called observer bias. As great as you can train anybody, observer bias is something that happens when you're dealing with categorical data, which is why we typically will use a meteorological station when we're looking at different sorts of weather patterns and like rainfall, wind speed, wind direction, so that you can eliminate the chance for that to come into play. But wind speed did seem to have a little bit of an effect on the levels of PM 2.5. Precipitation is another one to think about because there is something called, oh, and I'm going to forget the name of it. Let me look it up here. Wet removal, that's what it's called. Wet removal is basically the process that acid rain is formed in. You have these particles that are aloft in the air and you have rain falling down, right? And so as the rain is passing through these particles, some of these particles are going to absorb onto that water droplet and they're going to fall out of the air and onto the ground. And that's what's causing us to have, more acidic waterways. But it's also going to potentially reduce the amount of PM 2.5 that's in the air. And if you look at our precipitation, it does seem like when there's higher rates of rain, that there is less PM 2.5. Again, this is a discrete moment in time. This is precipitation as observed when these machines are being set up. And again, they are categorical. We're looking at rain, in this bin, which means no rain. This one, which means, however you want to interpret the way that we have the scale, that observer bias can come into play. And so you have to interpret these graphs kind of loosely because we're not looking at the same type of data. This is continuous data, this is categorical data. They're two, it's like apples and oranges. So comparing them, you just have to kind of take it with a grain of salt, if you will. Cloud cover, I don't see a whole lot of relationship here, and I don't see any reason why there would be any sort of relationship, but we do collect the data, and we do want to look and see whether or not there is any sort of relationship, loose if anything, and temperature, forget it. It's all over the place. It's the R, look at this R squared value. If you want to be close to 1, that's as far away from 1 as you can get. It's teeny tiny, not fantastic, in my opinion. So anyways, there we have it. We have some statistical significance thanks to the hard work of staff. We now have answered our question, and we're going to continue this study into next year. But what does the future hold? The thing about looking at PM 2.5 is that yes, we understand that there is more PM 2.5, but what's that made of, and how does that matter? We're not looking at the composition. Now, the Park Service has been looking at the composition of the air quality here in Skagway for the last 30 years or so. They've done lichen studies where they've taken little samples of arboreal lichen plots and they've sent that into a lab and they've put it into elemental analysis to look at different types of metals that they found in there because they're a really great indicator of air quality. And then they've also set up these little deposition collectors where they're looking at, partnered with the city, they were looking at sulfur and nitrogen compounds, which are typically associated with the burning of fossil fuels. And in a nutshell, what's been found is that over time, these sulfur and nitrogen compounds have been increasing. And my guess is that if you were to correlate that to the number of ships and the number of transient folks that are coming through town, there would probably be a relationship in that curve. So this all warrants further study. It's not continuous data what the Park Service is doing. We're not looking at compounds in our study. In an ideal world, what we would do is we would have a permanent network of monitors that are continuously sampling for a multitude of different pollutants and then are displaying those data on a public-facing dashboard so that if Sarah wants to go out one day, but she's concerned about her exposure to a certain type of pollutant, and I'm looking at going out one day, and I'm concerned about a different type of pollutant, we can both make independent decisions based off of real-time data that's quality assured and that's collected in a way that's scientifically sound, right? Beautiful thing. Fortunately, looks like this is actually going to happen. This year, we applied in partnership with the Park Service and with a partnership with the municipality. We applied for a pretty hefty grant from the EPA. It's called the Enhanced Air Quality Monitoring for Communities Grant. We were one of 4 entities that were awarded in the state. This was a nationwide competition, very, very, very competitive. I think 156 recipients all throughout the whole country got this award. And So the Park Service helped co-author the grant, and they're offering their technical support and their equipment. The municipality of Skagway is offering their equipment and access to municipal land for locating these nodes that we're going to set up. And basically, here's the plan. Right now, we have an existing network or a proposed network of these particulate monitors, these laser photometers, right? In the yellow, you can see the STC particulate monitors, right? This is where we have our stations. And then in the green, these green circles, these are where the Park Service has set up little purple air monitors. And the red is where the municipality is proposing to set up their purple air monitors. And so what we're going to do is we're going to pump up these monitors because consumer grade's great and they do provide some data, but we want to get down to a little bit looking more at the compounds that are inside of these things. Not just the particulate matter, but what is this particulate matter made up of? So what we're going to do is we're going to take all these locations, right, and we're going to outfit them with these machines. This one is going to be the brain. This is called the AQ Sync. This is looking at carbon monoxide, carbon dioxide, ozone, all the different nitrogen oxides, 3 different classes of particulate matter, and the MET stands for meteorological data. So all of these, every single one of these is going to have a meteorological station added. So we're going to have, what is this, 13 different meteorological stations positioned all throughout Skagway that are going to be continuously collecting data on wind speed, rainfall, relative humidity, all of that stuff that we were just looking at once a day. So we're going to have those data. But they're also going to be looking at all of these other internal compounds. And what happens is this brain is actually going to be connected to all the rest of these nodes. So everything will be communicating back to this central system, and then the data will be beamed out by a cellular signal to a central location where it will be pulled, it will be quality checked, and then it will be beamed back into a public-facing dashboard that anybody in the public can then access, look at, get real-time data that's been quality assured, and make decisions about their exposure to different types of pollutants throughout the day. It's very, very exciting. We're going to be starting to work on this next coming spring, and keep your eyes out because we're going to be looking for as much public input as we can. What do you want measured? How do you want the air quality index to look? How do you want the actual interface to look? Do you want it to be on an app? Do you want it just to be on a desktop? We want to know what the community wants in terms of the dashboard and this network, because it's there for public health, it's there for everybody else. So, probably the most excited that we are, since STC is going to be in charge of maintaining this network, is we are getting ourselves some e-bikes. We want to reduce our carbon footprint, so we've been approved to pick up a couple of these Pebbles. They're electronic bikes, they are pedal powered, but they're also battery powered. And so we'll be cruising around on the streets on these things. So keep your eye out for that. It's going to be super fun. And you guys have been fantastic. You've sat through a whole bunch of science, a whole lot of stats, a whole lot of torture. And here's some gumbo for you. He's the ambassador of air quality here in Skagway, the official, and happy to answer any questions anybody has.